And I have then, and let me play some music just to have some sound, and then we'll be ready for the speaker to join. When boy 1986. Is the same thing that I did today. Okay. So I trust that the sound makes it. Okay, so can you please write in the chat if you heard the sound, if you heard the sound at all? Let's write in the chat, yes, no.
Yep. Heard
Wonderful.
the sound.
You can hear the sound. So now we're waiting for the speaker very quickly. Before the speaker is connecting, you may have seen this before. It's all class, and at some point, yeah, there were no problems. C290 quantum. And if you go under what's new, that's the link. The thing is here, and I have this for later, right? This is an interview with her, 3 minutes, 5 minutes.
Are you having trouble trying to keep up with your professor? You've got to try Otter. Here's how it works. Let's say I'm in.
Hello, my name is Maria, and I'm a third-year physics undergraduate at Magdalen College in Oxford.
So Magdalen has a special spelling. She's no longer third year. She's a PhD student. I will introduce her when she comes. This is the link to her website. I'm gonna write down participants shortly, and then I was able to put here, and I'm gonna tell her too, a link to a video that has some of the information. Quantum bomb tester.
Imagine you are given a box and you can't see what's inside. All you know is that it is either empty or it contains a highly sensitive bomb. If this bomb is hit by even a single photon, then it will explode. Your challenge is to work out whether or not there is a bomb in the box without the bomb exploding. Classically, this is impossible. As soon as you try and detect the bomb will interact with your detector and explode. But in 1993, quantum physicists Avshalom Melitzer and Lev Weidman proposed a quantum bomb tester, which allows us to see a bomb without looking. Hi, I'm Maria, and I am a PhD student doing research into the foundations of quantum information at the University of Oxford.
So she's going to join soon. We have links to her paper where this is described. We also have links to the playlist that she has put together, Quantum Paradoxes, thought experiments with Qiskit. So now we're waiting for the speaker to join. What time is it? 8:46. So that should happen any minute now. Thank you all for coming today, and now I'm going to write down the list of people who are joining a little bit later. So I'm also going to connect from one other computer just to make sure that she's not having any trouble connecting. So we'll now wait a few minutes until she can connect. She may connect at 50 or 55. I already went, this is being recorded already, so I already went over the little things that I posted before she joins. So let's just wait a little bit. All right, so let's see, we're waiting a little bit now, so, Scott, Christian Scott, good morning, yep, yes, whatever, and, we have 14 people, that's very good, and we have, 2 people here in this room, and we're waiting for the speaker to join. And there she is. All right, so let's see. Can you hear us, Maria? No, she doesn't have a microphone yet. Well, maybe, who knows? There's the connection. So how are you, Maria? Hello, hello. We she connected? No. Let's establish some kind of connection. Can you hear
Hi.
us? Oh, good to.
Yeah.
Wonderful. So this is what is today? Today is Wednesday, July 10, and we have the pleasure and the honor of getting a lecture, a guest lecture live from Oxford by Maria Violaris, and it's 8:50, so we're gonna get started now. I want to say a few words about her, and then she's gonna take it away. This is the first of 3 lectures that she had a kindness of agreeing to. All lectures are gonna be on Wednesdays. Today is Wednesday, it's 8:45, 8:50 now. The other 2 Wednesdays a week from today, and then the last Wednesday of the semester, there will be 2 more lectures. So if you are going to the website, you will see her here. This is a picture along with other important pictures in other pictures on in the course. Now, just very quickly on this in this particular splash. We have 2 people that work with Maria. So this is Maria, and as far as I know, her dissertation is one of the people that are guiding her dissertation is Arthur Eckert, which appears over here in the queue from IBM Quantum, which they no longer use. And then another person that he works with is David Deutsch, that appears over here from the transcription of the videos on quantum computation that we posted. And if you click on this and go under what's new, the link to all the abstracts is here, and the link to today's class is here. This is a picture from 2021. And the link here takes us to the video where she's answering 5 questions. And
Who is Teachers of Tomorrow? Teachers of Tomorrow is the largest.
Hello, my name is Maria, and I'm a 3rd-year physics undergraduate at Magdalen College in Oxford. So
I'll let you watch that on your own. She will basically add to it by the presentation today. This is a website that she has that you can look through, a bunch of videos over here that are interesting. The title and abstract for today's presentation is here. I took from that website a link to the Minesweeper.
imagine you are given a box and you can't see what's inside. All you know is that it is either empty or it contains a highly sensitive bomb.
The question is, can you detect a bomb without interacting with the bomb? If you interact with the bomb is going to explode. This is the abstract. There's a paper that describes the workshop, and then there's a link to the playlist of quantum paradoxes that will somehow show up in these talks. Now, I'm going to stop sharing, and I'm going to ask Maria to share if she doesn't mind. There you go. So can you share and start, please?
Yeah, thanks for the introduction. I'll share my slides. Okay, can you see the slide?
Yeah. Yeah, that's good.
Okay. Yeah, so shall I get started?
I think so, if that's okay with you.
Yeah, great. Yeah, thanks for the the introduction and gathering all the resources on the website. So yeah, thanks for inviting me to give these talks. So yeah, I'm planning to give 3
lectures about aspects of quantum science and technology, using this centered around different thought experiments and implementing those thought experiments on quantum computers. And the one I thought I'd start with is the quantum bomb tester, which is, yeah, the one that was in this video. And I think it's one of my favorite thought experiments in physics. I think it really shows some of the most counterintuitive aspects of quantum physics, but it also translates nicely to thinking about quantum computing and the building blocks of quantum computers. So I think it's quite a nice thought experiment for bringing these fundamental science and technology aspects together.
So can I just ask just one last thing?
Yeah.
Out of excitement, I've got to mention something which I actually mentioned to you, but I want to mention it so that it's in the recording and everyone knows that we talked about it. So this is a class here at IU, Indiana University's second summer session, and we've been offering this for 3 years now. The purpose of this class is to be a bootcamp for our it's new because in 2021 is when it started, Accelerated Masters in Quantum Information Science, which is a program that's aimed at students that have undergraduates, that have graduated. They're graduated and they want to do a master's. They are STEM students, but they're not necessarily physics students. That's the bootcamp. And we do a number of things. This year, for the first time ever, we have like 3 graduate students, 10 undergraduate students of the kind I mentioned, some of computer science. And then we have 10 teachers, high school teachers from all across Indiana, where we are trying to, with sponsorship from our Center for Quantum Technologies, which is an industry center because it's supported with NSF and industry funds, but created by 4 universities in Indiana: Notre Dame, Indiana University in Bloomington, Indiana University in Indianapolis, and Purdue. With sponsorship from that center, we have 10 high school teachers. I want to say that unlike in the UK or in Canada or pretty much elsewhere, quantum topics are not part of the curriculum at a high school level, except in 2 states. One is Texas, of all Texas, thanks to Karen Jo Matzler in physics, high school. And then the other one is Ohio, that put the quantum topics in the computer science curriculum. Is John joining? All the high school teachers that join us today are computer science teachers, but then they have different backgrounds, including physics. So as you go along with your presentation today and then in the other 2 Wednesdays, this is the audience that you have, and they will probably ask questions. And then ask the people when they ask questions to briefly introduce themselves and just say what kind of the audience they belong to. And that's the context, and sorry I took so much time. Thank you.
Yeah, great. Yeah, please throughout the presentation jump in anytime with the questions so we can make sure things are clear and questions are getting answered kind of live. And I also wanted to ask, so I know that the course has been happening for some time already, so has some of the basics of quantum computing been covered already before, or
Yes,
just have an idea of that? Yeah.
This course is mainly using the Misty State formalism from Terry Rudolph's book. Terry says that he wrote this book to present to a group of people 12, 14 years old that Pete Shadbolt had in a summer camp in London, I'm not sure when, 2017. So his entire book is made out of Hadamard gates and control NOT gates, basically. And he says there's a paper by Xi that you can use to prove that this is enough. I mean, it's complete, and you can approximate with those gates that he uses in this book and his system pretty much anything. So the system that he's using doesn't use any numbers. It just uses black and white balls and a rule to combine them, whereby if I define a gate, I actually give you the slices of the matrix that defines that gate. Our goal in this class, at least this year, is to introduce all the concepts that people need to know to appreciate quantum mechanics through quantum computation, because there the model is very clear, and you don't have to solve equations to think about how you can apply your knowledge of physics. So we have 6 cases of quantum advantage. So far we have done phase kickback after introducing superposition and interference phase, later entanglement in 2 qubits, but 1 qubit case, 2 qubit case. We then looked at phase kickback. We did Berkeley Maserati, we did Deutsche, and we are in the middle of doing Grover. We are going to extend the system to actually allow amplitudes in front of the black and white walls, and then we are going to do teleportation. Super coding doesn't need anything special, and then teleportation, and we're going to end up with a GAC game. That's the class. We are in the middle right now. But they have done programming, I think, in Qiskit significant, and I think if the kind of discussion that you are going to put forth today is essentially like the Minesweeper video, they will be able to understand it.
Mm-hmm. Cool, great. Yeah, great. So we can get started. So yeah, so we've already had an introduction, but just wanted to briefly introduce what my background is. So at the moment I'm finishing my PhD at Oxford, where I've been researching the foundations of quantum information. So looking at very fundamental questions about things like the hour of time and irreversibility, how that connects with quantum mechanics, and also looking at various quantum thought experiments that are kind of like Schrödinger's cat, but more complicated versions, and then trying to reason about how they make sense
Maria,
and how quantum mechanics make sense. Yeah?
I have a question exactly to that. So, because the irreversibility of time, right? I mean, I'm not a physicist. I'm actually a PhD student in bioengineering as a major, and I have a minor in computer, on the major mainly computer engineering. I'm just in the second year. So, and I read a popular science book from Ilya Prigogine, and he exactly talks about the reversible of time. And he says the problem on quantum mechanics is that when you measure, that the entropy actually gets decreased, but usually when you measure the entropy would stay the same or get higher. So this is totally counterintuitive, and like that you have reversible, you have it reversible, the whole quantum mechanics, and it's not in reality. And he said that all these things that we know about parallel universe, and so they are just nonsense because we don't look at the reversal, that it's not reversible. So I would actually, because you PhD in that subject, I would love to hear more about what you think about that and how you can explain. Maybe you can say something about entropy and what we have in quantum mechanics, and look at the classical quantum mechanics. But I mean, this is my own interest, and of course there are other people here, and maybe this should not be the main subject, but just because you mention it here, I'm very interested to hear your thoughts about that.
Cool. Yeah, so a brief comment I can make is that depending on so there's lots of controversy about whether measurement in quantum mechanics is reversible or irreversible. And so there are some theories that measurement is irreversible. Others would say that it's reversible. And this problem comes up in the Schrödinger's cat thought experiment, and also in some of the thought experiments that I'll talk about in the later lectures, where it actually becomes really the difference between the measurement being able to be reversed or not actually has testable consequences. And sorry, this is how this aspect is actually related to how quantum computing as a whole idea came about in the first place. So that's something I'll talk about in a thought experiment in the next lecture. But we'll see in this one as well how we can model measurement in a completely reversible way in quantum theory. So yeah, I'll mention when I talk about that later. And then the kind of issue that I've been looking at in my PhD has been okay, if everything is reversible in quantum mechanics, because we're in this, if we apply quantum mechanics to large scales, then everything becomes reversible. Then how is it that we get irreversibility emerging? Is it just an approximation that we get on large scales that we can scramble eggs but not unscramble them, but it depends on having loads of particles? So that's the type of question I've been working on, and what I can do is send some links to content explaining that in more detail, and we could also discuss it more if there's time in the later Q&As or at the end of the lectures.
Okay.
Yeah, it's an interesting topic.
Nice. Yeah.
So and just briefly, the other things that I've been working on, I've done some internships with quantum computing companies. One of them was making this video series about quantum paradoxes. One of them was making this Raspberry Pi quantum computer simulation. And I've also worked on various kinds of public engagement, and recently started this Quantum Foundations podcast on my own YouTube channel. So if anyone's interested in that, I'm trying to have one video explaining things in a non-technical way and one video explaining them mathematically. So whichever level is best, hopefully the ideas are accessible. So the kind of unifying aspect of a lot of the both my research and education work is kind of trying to resolve paradoxes, and I'm always interested by situations that seem paradoxical, but then we find these satisfying ways to explain them. So that's a kind of unifying theme which will run through these lectures as well. And to summarize what will come, so today I'll focus on the quantum bomb tester and how that relates to these basic components of quantum computing that I think you're familiar with already from some earlier parts of the course. Then in the next lecture, I'll focus on these, I guess, quite fundamental thought experiments, the famous Schrödinger's cat, the double slit, and ideas about the measurement issue and modeling observers using quantum mechanics. And this is where the irreversibility of measurement becomes important, and we can see how we can get really satisfying explanations for resolving the counterintuitive aspects of these thought experiments. And then in the third lecture, we'll kind of go beyond into starting to connect with different disciplines, from the fundamentals out to connecting with other ideas. So I'll discuss some aspects of how we connect with relativity, because there's these things in these issues in special relativity about whether you can have instantaneous influence, and this becomes relevant when thinking about entanglement. Then there's this thermodynamics thought experiment with Maxwell's demon that I'll talk about. So that's also related to entropy issues. And there's some open questions around having time loops and time travel being consistent with quantum mechanics. And in all these cases, we can present. So I have videos from that series relating to each of these thought experiments, translating them to quantum circuits for quantum computers. So each of them kind of can become a quantum computing activity that you can do yourself. So for this lecture, I'll explain the quantum bomb tester, how we can effectively see a bomb without looking using quantum mechanics. I'll give an initial version, which is a bit dodgy in that it doesn't work every time, and then I'll explain a version that works every time. And then I'll explain how we can map it onto a quantum circuit that you could run on a quantum computer. So what is the quantum bomb tester? I like to explain the setting using a chocolate orange. So this is a chocolate orange we have a box with this inside. So for this thought experiment, we're going to pretend that this chocolate orange is a bomb. And I want you to imagine that you have a box which may or may not contain a bomb inside. And your challenge is to figure out whether or not there is a bomb inside the box without the bomb exploding. Now, the twist, the difficult thing, is that this bomb is really, really sensitive. So if even a single particle, a single photon interacts with it, then it will explode. So you can't just, so if you have it in the box, you can't just throw a particle in and see if it bounces back or not to see if the bomb is there, because it'll definitely explode if it is there. So using classical physics, there's no way to figure out if there's a bomb in the box without the bomb exploding if it is in there. And the amazing thing about quantum physics, or one of the cool things about it, is that we can actually figure out that there's a bomb, whether or not there's a bomb in the box, without the bomb exploding. So how is this possible? We're going to use a system called an interferometer, which essentially uses a photon, so a single particle of light, and we use there's a component called a beam splitter, which is it's like a half silvered mirror, which means that if we send a photon through to the beam splitter, then it puts the photon into a superposition of going straight through and being reflected. So this is where the quantum part comes in, because we can create that superposition. And then, so we use beam splitters, mirrors, and detectors. So I'm going to explain now step by step how we use these components, single photons, beam splitters, mirrors, detectors, in order to figure out if this bomb is in the box. So let's see what happens if we just forget about the bomb for now. Just imagine we have this situation of having a single photon, we have these two beam splitters, and we have two mirrors. Okay, so we send the photon through to one beam splitter. It enters a superposition of being reflected and going straight through, so transmitted. Then it's reflected back from the mirrors. Both parts of this superposition are reflected back, and they meet at the second beam splitter. And what happens there is we get constructive interference between these two parts of the superposition. So the photon interferes with itself, and then they merge back into a single photon just going straight through. So if we have
a beam splitter is a Hadamard gate. Is that correct?
Yeah.
Okay,
yeah.
Good.
So it does it implements the Hadamard gate because it takes you from from your one state to a superposition of that state and another state. And it also reverses that when you put them back in. It takes you from that superposition back to a single one, just like the Hadamard gate.
Good, thank you. Thank you.
Yeah. So that's the what happens when you don't have a bomb in this setup. So what happens if you put a bomb into into the pathway of one of the parts of the photon's superposition? Well, what's going to happen now is that this photon is going to go into this superposition of being going down the top path and the bottom path. And when it interacts with the bomb, well, if the photon, so when the photon reaches the bomb, it's going to be effectively measured by the bomb, because if the bomb explodes, then that's a measurement saying the photon went down the bottom path. if the bomb doesn't explode, that's like a measurement saying that the photon went down the top path. So we have the photon reaching the bomb, and then its state gets projected into either the bottom path or the top path when it reaches the bomb. So this is the same as if you put a qubit into a superposition with a Hadamard gate and then do a measurement, and you have 50-50 chance of seeing one of two outcomes. So that's exactly what's happening here, is we have this measurement and it projects the photon into one of these two paths. So we have two outcomes that can happen here. One of them is that the photon ends up in the bottom path. And this is not good because it means that the bomb explodes. And that's game over because we were trying not to explode the bomb. But the cool thing is when the alternative happens. So 50% of the time, the photon just collapses into the top path. And let's see what happens. If it goes down the top path, this time it doesn't have this other part of the superposition to interfere with. So when it reaches the second beam splitter, it actually just splits 50-50 because we're back in this situation like if you apply a Hadamard gate to just the single state, it puts it into a superposition. We don't have this other bit to interfere with. So now we have the photon being split again, and now it could be detected at the top detector or at this detector on the side. Now, if you remember from before when we didn't have a bomb, so going back a few slides, you'd always get this detector going off. So now that we have a bomb, these two, when it goes down the top path, these two detectors each have a 50-50 chance of going off. If this one goes off, it's the same as no bomb, so it doesn't tell us anything because this detector could go off if there is a bomb, it could go off if there isn't a bomb, so that doesn't tell us anything. The cool outcome is if it actually ends up at this top detector, because this detection could only have happened if there is actually a bomb here. So I should have left the bomb sharing there. This detection could only happen if there is a bomb here, but the bomb hasn't exploded. So if we ever see this detection going off, then that tells us that there was definitely a bomb there, even without the bomb exploding. So that's the case where you send this photon through the box on the bottom path, and then you've managed to figure out that there's a bomb in this box with absolutely nothing interacting with it, nothing making it explode. So that's the kind of the exciting outcome of this thought experiment. So yeah, next I'll explain. So one problem with this is, all right, it works. It lets us do something that we can never do classically, but that thing we only get that outcome 25% of the time. So the reason for that is that 50% of the time the bomb explodes because the photon was projected into this bottom path. 50% of the time it went up to the top path, but then half of that time it was at detector 2, which is the one that gives us this inconclusive result. We can't tell it apart from having no bomb. But 25% of the time we get this outcome we want of detector 1 going off. So before I move on to explain how we can actually adjust this to get an 100% effective bomb tester, I can just pause for a second. Does anyone have any questions about this version of the bomb tester and how it works, why it works?
I'm curious sorry, I'm Christina Snyder. I'm a high school teacher down in Georgia, zooming in here. But I was curious if we know like the exact probabilities of like when we hit detector 2, is it 75% of the time we're hitting detector 2?
25% we get detector 2. So we get 50% bomb explodes, 25%
Oh,
detector 2, and 25% detector 1.
okay. And then that 25% detector 2, 50% of that time there could or could not be a bomb. Is that right?
So these are the percentages that I'm saying are the ones for if we assume that there is a bomb,
Okay.
and then we say, so let's say there is actually a bomb in this box, and I didn't know that there was a bomb, and then I'm trying to figure out whether there's a bomb in the box without it exploding. In that case, there's 50% chance that the bomb, which is definitely in the box in this thought experiment, I just didn't know. There's a 50% chance that that bomb will explode. There's a 25% chance that I won't be able to tell apart the situation from one where the bomb wasn't there. And there's a 25% chance that I actually figure out the bomb was there without it exploding. So this is in the case where in this setup, this is the probabilities for when the bomb is in the box, and I'm just trying to figure out whether it's there. If
I'm
we're
with
in
you
a
now.
situation,
Thank you.
yeah. So if we're in a situation where, if we wanted to model the probabilities in a situation where the bomb is not in the box, then we could do that by saying maybe, let's say we have a 50% chance of either having the bomb in the box or not, and then we'll end up with different outcomes.
I try to rephrase that if I understood it right. So if there's a bomb, then by the first beam splitter, we don't get superposition, or we get a superposition that directly collapses again because there's a bomb. And then on the second splitter, we get a superposition. And when we then measure, that's why we measure as well the first detector. But if there's no bomb, we have already by beam splitter 1 superposition, and that's why we never reach the detector 1 because it collapses there to detector 2. Is this somehow correct?
If you have no bomb, you get the superposition. The superposition is undone by the second beam splitter, and you always get detector 2. Yeah.
And if there's a bomb, I get a collapse, directly collapse, right?
Sorry, can you say that again?
Bomb of the splitter 1, I get a sort of superposition.
Yeah.
But then it collapses directly because of the bomb.
Yeah.
That's
Okay. Yeah.
Okay. Thank you.
Yeah, that's right. Yeah. The bomb acts as a measurement device which implements this this collapse of the superposition into just one of the states.
Hello, my name is
Cool.
Ben, and I'm a high school teacher as well as a physics teacher. My question is actually a physics question. When a single photon goes through beam splitter 1, before it gets measured, do we worry about things like conservation of momentum at this point, or not until it gets measured is the only time that we can really talk about those sorts of things?
Yeah, so do you mean because it kind of looks like momentum is not conserved, right? Because you start with the photon just going horizontally, and then now it's going superposition of horizontal and
during the
vertical.
superposition.
Yeah.
Is that a thing that we worry about measuring, or not until the photon is actually measured out of its superposition?
So in this situation, we're never directly measuring momentum, and I guess the momentum issues don't come into the kind of abstract analysis of the outcomes that happen here. But
Sure.
It's actually quite an interesting subtle point of how, like, basically I'd say it is something to worry about, of asking even without doing measurements afterwards, we do need to explain how is momentum conserved here? Like, that is a question that needs answering. And the answer turns out to be that essentially the way you can imagine it is, imagine this beam splitter made up of loads of particles. And if essentially those particles need to kind of move in the opposite direction to compensate for the momentum change.
Okay.
And what happens is, as you make that number of particles really large, so the beam splitter becomes kind of classical because it's made of loads of particles, then that effect becomes negligible. So we kind of absorb this slight momentum difference into the beam splitter being this macroscopic, effectively classical system that's made of loads of particles. And that's what kind of saves the conservation law. Yeah.
Yeah,
so
that's fine. I think this will probably take us off topic. So I appreciate it. Thank you so much.
Yeah, it's a good question that actually comes up in our research discussions, because conservation laws in quantum mechanics are also a bit of a subtle issue, when superpositions are involved. Are there any other questions at this stage? Okay, so we can have a look at how to make an 100% effective one, because some people might be unhappy with having a 50% chance of exploding their bomb if it's there. And so it's pretty cool that we can actually get this up to 100% effective. So how do we do that? Essentially, the mechanism is, so you can imagine this bomb tester setup that I described. Essentially what you do is you adjust the reflectivity of these beam splitters that I mentioned, and then you send the photon round this setup loads of times. And doing this lets you figure out whether there's a bomb with a much better probability of success. So now, to explain in detail why that works, I find it useful to visualize the photon going around this setup over and over again by kind of putting the setup, mapping it out in space. So in this diagram, I've basically each one of these is like going through the setup once, and then I've represented going through it again by adding another set of the beam splitters and mirrors again. So I've done this to try and make the explanation clearer, but what it's really representing is going around the same box over and over again. So what's happening here? So here we have the bomb here, and what we do is we make this, so this is the first beam splitter that our photon is going to go through, and we make the reflectivity of this beam splitter really high. So there is a really, instead of the 50-50 superposition we had before, now we've got a really high chance of being reflected and a small chance of being transmitted. So there's a very small probability that the bomb will explode because we've made this transmitted bit really small amplitude, but there's a high probability that the bomb will cause the photon to collapse back into this top path. So if it collapses into the top path, it reflects on the mirror, goes through the setup again. The next time, exactly the same thing happens. It has small probability of exploding the bomb, high probability of being collapsed back into this top path. So this happens again and again as it goes round the setup until we get to the final beam splitter. And now there's this very small probability of setting off the detector 2, and there's a high probability of setting off detector 1 at the end. So that's what happens if there is a bomb. And we can make this probability of exploding the bomb really small by making this amplitude of being transmitted through the beam splitter really small. So what happens if there's no bomb? Because we need to make sure that we have different outcomes for when there is a bomb and when there isn't a bomb for it to actually tell us something interesting. So this is, so maybe I can also mention on the previous bit, what we call this effect, that when you keep measuring the photon, it kind of stays in the same state. This is called the quantum Zeno effect. It's named after Zeno's arrow paradox, which is this idea that if you have an arrow flying through the air, how is it actually flying? Because at each instant it's stationary. And if you just kept observing each instant, then it's never moving. And this idea kind of inspired as an analogous name for this effect, where if you keep observing a quantum state, you keep measuring it, then it will stay as it is because it has a high probability of collapsing to the state it's in if you keep measuring it. So that's essentially what we're using here, is we're measuring this photon constantly with this bomb. If there's no bomb, then we essentially get a spread out version of this interference that we saw before. So before we had, you put the photon through and then it just interferes with its superposition at the second beam splitter, ends up at detector 2. This time, what you need to do when you have lots of these high reflectivity beam splitters is when you have enough of them, then your photon at each round, it interferes a bit with itself. And once it's interfered with once you've done this exactly the right number of times, then you end up with it interfering with itself back to the point where it's it goes straight through the final beam splitter. So essentially we're spreading out that interference that you saw in the original version into all these cycles with this high reflection version. So what you can see comparing these two diagrams is that if there's no bomb, we always get this detector going off. If there is a bomb, then you're very likely to get this detector going off. And you do have a small probability of exploding the bomb, which is bad, and of having a kind of false positive result that you measure a detector 2 going off and then you think that the bomb wasn't there when actually it was. So they're the two ways that this can fail. But the cool thing is that by adding more and more of these cycles and making that reflectivity of the beam splitter higher and higher, you can make that probability of failure as small as you want, which is pretty cool. So you can, whatever error you want to present your, however small you want to make your probability of failure, you can do that with this setup. So you can successfully detect your bomb without it exploding. So so next I'll talk about some of the implications of this, but I'll pause again. Does anyone have any questions about how this 100% effective version works?
Okay, so John, just a second. I want to ask the following question. You don't have to have a very powerful bomb to do this experiment. So if we have like something like a firecracker or whatever, do you know of anybody who has done this experiment? Just to, besides you in Qiskit, which hopefully you'll show, but it's been done in lab for real to just prove that.
Yeah, it has. Yeah, so in Qiskit, it's kind of mapped onto these superconducting qubits. So the physical setting is a bit different from this case where we have the photons. But people have done it kind of physically with this kind of setup of having an interferometer, having the photons in space going down different paths. And instead of a bomb, they have like an atom, and the bomb exploding will be the atom going into a different energy level. And so they have something controlled as a as the system that's in the place of the bomb, and something that indicates the exploded state where it's absorbed the photon or measured, where it's been affected by the photon.
Very good.
And
One has a question.
yeah, this has been done experimentally, and this paper that introduced this 100% effective version was actually an experimental implementation paper. It was the kind of experimentalists trying to implement this experiment that figured out this way of doing it to up to 100% effectiveness. So it actually came at the same time as the theory for this step.
Thank you. Thank you. So John.
I also had a question. My name's John. So it's one photon that's going through all of these beam splitters, or is it multiple?
Yeah, just
okay,
one.
So how does one photon, how can that like or how can it interfere with itself at the reflections?
Yeah, so that's the kind of unique quantum aspect of the so going back to this diagram, it's the kind of unique quantum ability of photons is this ability of being able to interfere with itself, which is really weird. And this is at the root of the double slit experiment, is exactly this effect of the fact that you can send a single photon through a double slit, and then when you observe the pattern on the screen on the other side, you see a distribution of outcomes showing that each individual photon that you sent through one by one was able to interfere with itself by behaving as though it went through both slits, interfered with itself, and then was measured. So this is kind of the fundamental weirdness of photons being able to behave quantum mechanically.
Yeah, that makes sense. Thank you.
Yeah, thanks for the question.
Yeah, I have a question. So in the multiple beam splitter case, I was just wondering why does that work 100% of times? Because I mean, there's always a possibility it hits the bomb, right?
Yeah, so technically it's never exactly 100%. It's always there's always going to be some probability of exploding the bomb, but you can make that probability as small as you want. So you can whatever error you want to be able to tolerate, or however successful you want to make it, you can do it just by adding more cycles. So there's always going to be a small chance of error, but the reason that I don't really find it concerning on a fundamental level that we always have that tiny bit of error is that you're in an experimental context. We have that always with every experiment. There's some probability of your measurement having given you a false outcome. There's physical errors in our components whenever we do an experiment. So you can imagine, let's say we have some experimental equipment to do these kind of experiments, which inherently has some small error in the outcomes that it will give you. And we could choose to do enough cycles here that the error we get, this kind of theoretical error we get, we can make it smaller than the fundamental, smaller than whatever our practical devices error have anyway. So in a way we can always make it smaller than the other errors that we can't avoid. So but it's never, you're right that it's never 100% effective. It's always up to 100% effective in that you can get as close as you like.
So Shivam didn't say, but he's a math major, which explains the difference in points of view. See, like 100% for him is 100%. End of story.
Yeah, there's some subtleties with whether you can do something. Sometimes there are these interesting situations where because this can't it is kind of interesting that there is no way of setting it up to make it exactly 100% effective. And a question that I think is interesting is if it was 100. Sometimes I'm thinking like, if there was a way to make it 100% effective exactly, would that violate some fundamental principle? Or is it just that we can't make our setup work that way? Or is there something fundamental about not being able to do it 100% theoretically? So yeah, there's kind of interesting conceptual questions there. Yeah, are there any other questions or comments at this stage? Okay, so this thought experiment is kind of cool by itself, but the implications seem to, yeah, become even weirder when you consider them in the context of quantum technologies. So, so one kind of direct implication is that you can imagine using these for this method for imaging, because you can detect something is there without it absorbing a photon. So if we have a delicate object like a cell or something really delicate that we want to image without, where even single particles interacting with it causes it to change in a way that we don't want to, then we could use this method to do kind of interaction-free imaging, and people have done implementations of this. And another cool aspect is it's called counterfactual quantum communication. So this is quite cool because what you can do is imagine this thought experiment of having, let's say, your two people that want to communicate, Alice and Bob, and normally they'd do that by sending some photons between them to communicate. And if you do a setup that's similar to this bomb tester setup, you can actually make it so that they can sometimes communicate a message from one to the other without the photon actually traveling between them, because you end up kind of, you can collapse into a state where the photon didn't actually travel between them. It just had the potential to travel between them. And this kind of seems to give you an advantage with security, because some eavesdropper Eve can't eavesdrop on a photon that is not there, right? So yeah, so there's this quantum communication protocol based on these mechanisms, and although it's a little, there's some debate about how exactly to be able to say whether a photon has been there or not in these thought experiments, so it gets a little subtle, but yeah, it's a kind of cool idea. And another one that's really hard to imagine is that this leads to counterfactual quantum computing, where essentially you do the bomb tester setup. Instead of having a bomb, you have a computer, and you say, I want to find out the outcome of running the computation without actually running the computer. And you can do this by putting the computer into this setup, and essentially you can collapse into a state where the computer hasn't run, but you've still retrieved the outcome of it. And again, you had to have the computer having the potential to run, so it doesn't save you having the same technology that you need usually to make that computer to do the computation. But it's yeah, it's kind of weird that you're able to find out the outcome of this computation without it actually having been run on your computer. So that's some of the weird.
Just a quick question. We owe this last one to Mitchinson and Georgia, how do you say the name of each other?
Yeah, Josa. Josa? Is that, yeah?
So it's the same Joseph from Deutsche, right?
Yeah, same one. Yeah, so yeah, they have this paper on counterfactual quantum computing. Yeah. Yeah, so as far as I know, I've not heard of anyone managing to turn this counterfactual quantum computing into a kind of practical advantage because of this fact that you still need the computer to be able to run the computation in order to do this. So it's not clear if there's a situation where it helps you with some practical advantage, but I think on a fundamental level, it's very counterintuitive that this is possible. And so it leads to some, especially in this setting where you can make it up to 100% effective, and you think, well, when was this computation run if it's only been in a very small fraction of the quantum state where it actually ran, in a similar way to how the bomb only exploded a very small fraction of the times. So yeah, it's quite weird to think about. But it is possible and it's been tested and things.
See,
I was
not following.
Yeah.
Everything that I'm reading. Why is it about like cells are biological cells, right? That make up a tissue, or that's what you think about, that they measure interaction free? Because on your first point, I think you froze.
Yeah.
So what is the point that they interaction free, or why they cannot? Because I mean, usually when you think about cells, you more think about something like signaling, chemical signaling, and the cells are oriented on a chemical signal or somehow something physical like a fiber that they orient on. So I'm still puzzling a bit why now thinking about contact-free cells. I maybe not hear everything that you said, but could you repeat that?
Yeah, so this application to imaging. So the general idea is, let's say we have an object that will be sensitive to single particles or single photons hitting it. So it might be damaged, for example, by something hitting it. And so we want to be able to image it in a way that won't damage the object. And then thinking about situations where this might be the case.
It's like microscopy.
Yeah, the biological cells.
Microscopy. Yeah, microscopy imaging.
Mhm.
Okay, I see.
Yeah, that kind of imaging. Yeah.
I get the point, but then I would have to think about it, because usually you use something like fluorescence microscopy where you anyway tag some of the proteins and so, but still, I mean, I see, I have to think about more about that. Thank you. Yeah.
Yeah, so that's yeah, people have done this experimentally. So yeah, there are papers where, for example, they look at using this technique to image various objects. I think they include, I think they have various objects that they show how to image them. And yeah, maybe I can send that paper over, might have more context. Yeah. Cool. Yeah, thanks for the questions. So yeah, another point which is brought up in the original paper about this bomb tester. So it was proposed by Avshalom Elitzer and Lev Weidman. So people call it the Elitzer-Weidman bomb tester. And one of the authors of the paper, Lev Weidman, argues that this thought experiment is evidence for the many worlds theory of quantum mechanics, essentially because this many worlds idea is to do with this controversy about whether when you measure the photon with the bomb, does it actually collapse just into one of the paths, or is it actually the case that both of those possibilities happen but in separate branches of the universe? So what's actually happened is the bomb has become correlated with the photon or entangled, which means that as soon as the bomb and photon interact, there becomes a version of the bomb that explodes with the photon in the bottom path, and another version of the bomb that doesn't explode with the photon in the top path. And so that's the multiverse interpretation is of the photon becoming entangled with the bomb and both outcomes happening, as opposed to the single world view where only one of those happens. And what Lev argues is that this thought experiment in a single world view is actually paradoxical, because how can you find out information about an object with absolutely nothing interacting with it, which is what happens in the single world view. And he says, well, no, you can't. You need the multiverse, because then you can say it did actually interact in this other universe. It caused it to explode. And so there was a physical interaction. It just wasn't in this part of the quantum state that I'm seeing. So I think they explicitly say in the paper that just one of the authors has this view, not both of them, which I think just goes to show that it's still it was and still is a kind of debated thing of whether this is evidence for many worlds, what kind of there's debate around these interpretations, and we'll see aspects of how these come into the thought experiments in the next lecture with Schrödinger's cat. But I think it's kind of cool that this thought experiment combines with thinking about these fundamental ideas about reality. So now onto the more practical side is how can we map this thought experiment onto a quantum circuit that we can then run on a quantum computer. So if you've used a bit of Qiskit, then this kind of coding might look familiar. But essentially the idea is to take this setup on an abstract level, so thinking about it in terms of qubits, and then take that abstract level setup and map that back onto a physical setup of, in this case, since it's coded with Qiskit, it's easy to then send it to the IBM quantum cloud computers and actually run it on these superconducting quantum computers. So how do we turn this photon moving here and here into a quantum circuit that you can code? Well, we've mentioned already this fact that the beam splitter acts as a Hadamard gate. So we have our photon, it has this Hadamard gate, and then so this qubit is representing the photon. Then we have another qubit representing the bomb, and this control not gate is the interaction between the qubit and the bomb. So this qubit, I'll explain in more detail why that's a C0 gate in a second. Then we have this second Hadamard is the second beam splitter for the photon. And then we have these measurements at the end to see, this one tells us is the detector of telling us whether detector 1 or detector 2 was measured. And this one is telling us whether the bomb has exploded or not. So, so they're the gates that we're going to use. And you can code them quite simply in Qiskit by adding the Hadamard gate, control not gate, Hadamard gate, and then doing a measurement. So
would you not need
just
on Q1, because sometimes you have a bomb and sometimes you don't?
Yeah, so here I'm in a setting where we're just assuming the bomb is there.
That's
but
awesome.
So let's say, So you could imagine a kind of, if the bomb is not there, then we'd remove this control not. And if the bomb is there, then we do have the control not. So, so I think in this, so I made this quantum minesweeper game where you have to try and figure out whether there's bombs without them exploding. And I think in that case, I made it so that the control not sometimes is there and sometimes isn't, so that you'll be in this situation where you don't know whether the bomb might not be there, the bomb might be there. So yeah, it's a good point that if the bomb is not there, we don't have this C naught, and then you'll just have these Hadamard and another Hadamard. They'll undo each other. You just get 0 here every time.
Okay, I get it. Thank you.
Yeah. So just for looking at the outcomes where the bomb is there, we look at this circuit. And yeah, so with IBM, that'll be run on quantum computers, and I just added some slides to summarize the basics of quantum computing, which I'll just go through briefly because I think you've been introduced to these already. So we have this information encoded on a qubit. So the 0 state here is our photon going horizontally. The 1 state is the photon going vertically. And then the photon going through the beam splitter is this superposition of 0 and 1. And you can imagine these on the surface of a sphere, where each point on the surface of the sphere is a unique quantum state, 0 at the top, 1 at the bottom, and every other point is a combination of the two. And I like to make my own block spheres. So this is called a block sphere, and you can make one yourself and rotate around. So the quantum gates rotate the states around this sphere from one point to another point. So the Hadamard takes you from 0 to the superposition and then back to 0 when you apply again. So that's and yeah, there's all these different ways of physically implementing them with photons, or with the different energy levels of an atom, or with different states of superconductors. But on an abstract level, we can describe these all in the same way in terms of qubits. So, and this is how quantum computers work, is having all these qubits, having them interact by these quantum gates, and then interfering to try and get the correct outcome to come out with high probability. So what happens with this photon case? So I have put a bit of maths here, but you don't need to worry about working it all out exactly, but I think it's useful to just see it laid out. So what we have is we have a state representing each qubit. We have our photon qubit, we have our bomb qubit. They both start off as 0. So the photon qubit is 0, meaning it's horizontal. The bomb qubit is 0, meaning it's not been exploded. Then we have our beam splitter is the Hadamard, which puts us into the superposition of the photon being in both paths, 0 and 1. The bomb is still not exploded, so it's 0. Now we have the bit I mentioned, I'd go into more detail. We have this interaction, the C0 gate, where the photon interacts with the bomb. So if the photon is 0, it's horizontal. Okay, this is maybe, I should have made it different to be unexploded, but essentially the idea is if the photon is horizontal, the bomb explodes. So we have one part of the state with the photon one way and the bomb exploding, and the other part of the state where the photon goes the other way, the bomb doesn't explode. So the C0 makes the second qubit flip based on the first qubit state. So that's why it acts as this measurement, because the second qubit tells us what happened on the first, tells us what state the first qubit is in when we do a C0. It's like a copy. It copies that information onto the second qubit. And when we do this other Hadamard, again to the first photon qubit, we end up with this final state having 4 possible states. And basically, we find in 2 of these states, the bomb has exploded, which is what happens with a 50% chance. And in 2 of them, the bomb hasn't exploded. In one of them, it's given us this inconclusive result of the detector 2 going off. But in one of them, we've had detector 1 going off, and the bomb has not exploded. So that's the outcome we wanted. So one of these 4 is the outcome we want, which happens with 25% chance. So yeah, that's the summary. And then I was asked to suggest some things that you can do to kind of further engage with these ideas. So just a few things that you could try if you want to think about these ideas more is one of them, you could try and explain this thought experiment to someone else, because it's quite fun. And if you can draw out the diagram and explain the different possible outcomes, it can help to process exactly what the weird outcome is and exactly what the quantum effects are enabling you to do that's so different from what you can do with classical physics. Another thing you could do is there's a cool platform, I don't know if you've come across it, called Quantum Flytrap. It's an online virtual platform where it's kind of based on photons, and you can drag and drop different components to make setups with this kind of thing. And yeah, you can basically drag and drop these components to make your own simulation of a bomb tester thought experiment with the photons. So it's quite a nice platform for playing around with these kind of photon interference things. So yeah, that's something to check out if you want. And if you fancy doing some coding with Qiskit, then you could code that circuit that I showed yourself, and figure out which state is the one that tells you the bomb has exploded. No, tells you the bomb is there without exploding. And alongside my video, I have this code tutorial going through the code, so you can refer to that if you want as well. And in that tutorial and in the video, I also made this quantum minesweeper game where you don't actually know if the bomb is in the box or not. And then you can basically make this more effective version by adding more cycles, and you can get a score on how often you've predicted correctly whether the bomb was there or not by, and you should get a high score when you add more cycles on average. So if anyone wants to try that, you can have a go and tell me your scores. I will give a slight heads up on these code tutorials that I made them a while ago, and I'm not sure if the new versions of Qiskit will throw up any errors, but hopefully the circuit diagrams should be enough to reconstruct what was going on, and to, yeah, hopefully it still works. So yeah, just to summarize, we have the quantum bomb tester lets us see bombs without looking. We can make it up to 100% effective, and we can turn it into a quantum circuit with these basic building blocks of quantum computing, Hadamard's, C-knots, and measurements. And we get this entanglement after that Hadamard gate. And yeah, I think we're near the end of the session now, but I'm happy to take any more questions. These are the links to the quantum bomb tester content, and this is a link to the paper that was mentioned about, yeah, I guess that these lectures are kind of inspired from, and some links to my contact and other content details. And yeah, that's all for
Excuse me, I
today.
have a
So yeah, happy to take more questions. Yeah.
Yeah, I'm Carla Gelhausen. I'm a high school teacher, a virtual high school teacher in computer science. And so my question is, will you make these available, the slides available to us so that we can go back and look at them and have the links? Because these links are pretty cool. So I just wondered if, okay.
Yeah, I can send them. Yeah, I'll send them over and figure out a way to share them.
Or at least share the links so we could get those, because that would be neat to do, like the different games you were talking about. I'm thinking about my students. See, I'm a high school teacher, so I'm thinking it's got to be fun, or they don't want to do it.
Yeah, I reckon we can, maybe add the slides as an attachment on those web pages for the course. Yeah, I can also send the links on the chat here if I can figure out how.
Thank you
yeah.
so much. That would be so awesome. This was really good. I enjoyed this.
Yeah, that's
Thank
good to
you.
hear. And yeah, and I guess, yeah, in general, on my website, I have a quantum paradoxes page, which has links to each video blog and code tutorial. So that's also a more centralized place for finding the resources. But yeah, I'll make sure that the the slides are shared with everyone somehow.
Yeah, and I'll type all those links in just to make sure that they're still active and then let you know if any of them is broken. But now we got to the end of today's lecture, so thank you so much. We enjoyed this a lot. I think we're gonna look forward now to the one next Wednesday.
Cool, great. Yeah, it was fun to chat. Thanks for all the questions. Please keep them coming in the future lectures because yeah, it's really good to have those as interaction, and yeah, look forward to seeing you next week.
Very good. See you in a week. Thank you so much once again. Bye-bye.
Thank you.
Bye.
Oh, yeah, I put you there because why not? So you were asking, talking, and why not show up? Look at you, you're there. All right, well, thank you so much, everybody, and we're going to stop recording and then I'll post this at the later.